Thanks, Andy, for the introduction, and thanks for having me here as well. So, yeah, my office was just over there and up a few floors, so it's kind of quite nice being back in my manor. But I was hoping to see a few more familiar faces, actually, but I think people in government move on so quickly that hopefully there's lots of new faces and new people to meet today. So I worked primarily on the IPCC report on Chapter 2 on land-climate interactions. I'm going to cover some of the introductory material from Chapter 1 and the Chapter 2 stuff. And the main point to make really is, as with all systems, land is at extreme risk from climate change, but it also contributes to climate change. So there's a two-way process. And so how we manage the land to mitigate climate change and both adapt to climate change and do both those things together is really, really critical moving forward. So I'm going to show you some data on the threat that climate change poses to biodiversity and just touch on food production because Andy's going to come back and talk a lot more about food. I'm going to show you that the land sector, the agriculture and forestry, contributes about a third of all greenhouse gas emissions currently. And I'm also going to show you some potential options for mitigation, but the land is limited for how much we can mitigate on the land. So we still need to do everything we can in other sectors. So climate impacts on the land. This is actually from the 5th assessment report. It's showing you the change in temperature, precipitation, and sea level, and two different scenarios, these representative concentration pathways. There's basically the 2.6 scenario lands you up roughly between 1 and 2 degrees, and the 8.5 scenario between 3.2 and 5.4. My mic's going a bit. Can you still hear me at the back? Even when, now I'm all echoey. Spooky. And what I really want to say about this is the changes aren't even everywhere. So land is warming faster than the oceans, and northern areas are warming faster than the equators. And both poles are warming faster than the equators. And also we see with precipitation, you've got some areas where you've got increased precipitation and some areas where you've got less precipitation. All that means uncertainty about where food production might increase or decrease, uncertainty might happen with where species are able to cope. And sea level rise also rising, but I'm going to leave that to this afternoon's talks. As well as the temperature and changing in precipitation, those maps were just showing you the annual average. You also have an increase in frequency and intensity of extreme events. You have the CO2 fertilization effect, whereby the extra carbon dioxide we've put in the atmosphere is actually beneficial to some plants in some places, although other things might limit. So you actually get a promotion of plant growth due to CO2 fertilization in some places, and maybe due to more favorable conditions. And you also get a change in distribution of pests and disease. So all those different effects in different places means that we've actually got biome shifting, so movement of where we expect ecosystems to be. And this map is just showing lots of places where there's been studies that show that. But in general, what we're seeing is a shift of climates and a shift of biomes associated with those north and south, and an increase in dry climates and a decrease in these polar regions with a shift of the forests north. And sometimes those shifts are happening so rapidly that it's really hard for species to adapt, and that's when you start risking loss of biodiversity. And I don't know if any of you also saw a really incredible detailed report that came out this year, the IPBES report. That's the Intergovernmental Panel on Biodiversity and Ecosystem Services. And that's a similar assessment report that the IPCC ones. And there's a wealth of information in there, so I really suggest having a look into that. So we're likely to get new hot climates and loss of some climates that are critical for certain types of species. Now these maps, these figures, if you're familiar with IPCC, you'll be familiar with those, but if not, I'll talk you through them. They kind of show burning embers, that's right, that's what they're called, isn't it? Burning embers. And what they're showing you is the kind of impacts you might expect at different levels of warming. So we've got here 1, 2, 3, 4, 5 degrees. This bar in grey that's going across is showing you what the current temperature is above pre-industrial, and you've got a little dotted line showing you 1.5 degrees. And it's looking at across different systems. The laser's coming and going as well. I'm not doing very well with my tech, is a bit weird on me. But actually what I'm going to focus on is not go into all of those, but I'm just going to focus, because Kat's going to talk to you later about dryland system, and Andy's going to come back and talk about food. So I wanted to pick out these ones, which is the vegetation loss, wildfire damage, and permafrost degradation. And you're seeing the yellow line means kind of moderate. You see some changes in some places. High, you expect these changes in most places. And very high, you're starting to see sort of really intense change and some irreversible effects. So you can see for wildfire damage, for example, you've got moderate effects already, very quickly building up. And we know, because we're seeing the fires at the moment in Australia and California. And here we go. Here's a detailed look at wildfire damage. At about just over 2 degrees, you get a 50% increase in the area burned in the Mediterranean, and up more like above 4 degrees, you've got over 100 million people affected, additionally affected because of fire. And I just wanted to touch on that fire, because one of those other ones as well actually was loss of peatlands. Permafrost degradation there in the north, where you get the ice melt and permafrost degrades. Both of those release greenhouse gases to the atmosphere. And this was in the news this morning on the BBC website, rather handily, or quite depressingly as well. The fires in Scotland last year, there was 6 days burning in the high flow country, and the entire emissions from that were equal to all of Scotland's greenhouse gas emissions for a year. So there's lots of feedbacks as well between land and climate change. So impacts of land on climate, that brings us very nicely to. This is just really showing you about what the different, how we're using the land, what the land surface is used for. Lots of cropland, lots of pasture. And this is the number I want to highlight. Only 16% of land is considered to be in minimal land use. So not really being used for anything particularly. And that is important when we look at the scenarios later, which talk about the mitigation you could do on land, and they assume a certain amount of available land. So there's actually not very much land available, and I'm sure that is being used for things anyway. It's not like nobody's doing anything with it. It's not important for wildlife. So as well as the land cover changing, we've had a massive spike, so big it doesn't fit on the same graph, 800% increase. There we go. Oh my God, more echoey. Lovely. 800% increase in nitrogen fertilizer use. And here, number 3 down here, we've got an increase in irrigation, water volume. This one's not working. And all that's been great, because it's actually resulted in a 200% increase in cereal yield, which is actually really helpful to feed people. There's also an increase in ruminant livestock, and those things are important because inorganic fertilizer produces nitrous oxide greenhouse gas, and ruminant livestock produces methane. And so what we see, these are the emissions from the land sector. This top line here, number 1, that's the CO2 emissions from 1961 to 2016. That's a net. The land is both a source and a sink for CO2, but when you add up anthropogenic deforestation, afforestation, all the anthropogenic activity that's going on there, that's the net CO2 flux. And this is methane. So 13% of carbon dioxide comes from anthropogenic use of land. 44%, nearly half of all methane comes from agriculture, and a whopping 82% of all nitrous oxide emissions come from agriculture as well. And if you add in energy to that, then you've got a whopping even more emissions that are associated with the food system. At the same time, the land is also a sink for CO2. It actually takes up almost a third of the CO2 we produce as a natural response to climate change and CO2. And that's a really good service of the land that's also under threat from future climate change. And one of the issues we've got with these numbers actually is they're very uncertain. It's very uncertain because of what we know about the data, but also the approach to measuring it. So this is the number we get from global models that I was just using there. This red line is from two particular types of global models. But this is what the countries are reporting in their greenhouse gas inventories for CO2. And there's a big difference. And that has implications when we come to do the global stock take under the Paris Agreement. But the good news is we know why that is. And it's because of a different approach to dealing with this environmental change flux on managed land. So understanding that is going to be important when we come to do the global stock take, so that we don't think we're doing better than we actually are and take our foot off the gas pedal a little bit. So I'm not going to dwell too much on the agriculture other than say most of the methane is coming from ruminant animals, and most of and then the nitrous oxide comes from really fertilization, both from artificial fertilizer and manure. So how do we respond to this? We have all these pathways. You might have been familiar with these from the 1.5 report of how we get to 1.5 degrees. We have to bring down our grey fossil fuel emissions as much as we can. We also need to bring down our net emissions in the land sector, agriculture and forestry, and move towards having net removals. And then this is bioenergy with carbon capture and storage, where you're growing, pulling CO2 out of the atmosphere, then producing bioenergy, capturing the CO2, and sinking it underground. Is it better if I just stand away from you? A bit better? No. Coming in and out. So that's one way of doing it, and there's many different pathways. There's many different ways you can get to 2 different degrees. Many different features where you can have very little bioenergy or an awful lot of bioenergy delivering you those CO2 removals. But in the scenarios with high bioenergy, you've got up to 750 million hectares of land being used for bioenergy, which is an area about the size of India. If you have less bioenergy, you end up with more forest use, and some of these assume an increase in forest area, some assume a decrease in forest area. So across the different scenarios, you've got forest area changing from 200 to 7,200 million hectares. So it's really variable what we do on the land, but the important thing is how much land do we actually have available. And this final figure is looking at mitigation from different options. And I know it's small, I'm going to blow it out in a minute, but just so you get the rough size. All of these are different literature estimates, all the little dots. We've got different options in agriculture, in forestry, different options for carbon dioxide removal and demand management. And I just want you to see, first of all, just the relative size, because some of these really big ones are reduced deforestation up here, afforestation, reforestation, BECCS, bioenergy with carbon capture and storage, and biochar and other ones. However, not all of these are additive. You can't add all these up. Many of these ones here are competing for land with each other, as well as with existing food production. And so that was just a little bit of a closer look, really, at some of these really big ones where you've got afforestation, deforestation, reforestation going off the scale. You've also got forest management, wetland restoration, biochar, as well as BECCS, and many other options in there. So that brings me back finally to my key message. What you do with land is really, really important. Reducing emissions is key, but actually we're still going to remain with some emissions if we want to be able to feed people. So it's this combination of still managing to feed people, adapting the land so that we can feed people in the face of climate change, but also mixing that with mitigation options that are sustainable, because there's only so much we can do on land and it's very precious. What we do really counts. Thank you.
Rachel Capon, you talked about afforestation and deforestation, and you also talked about scenarios with BECCS. Now, obviously, with BECCS, you're planting more trees but harvesting them. I was wondering, is it actually better to plant the trees and harvest them, or just plant them and leave them to grow?
That's a really excellent question, and it depends a bit actually on where you are. So there's more of a question for me about actually where you've already got trees. People talk about cutting trees for bioenergy. Obviously, you don't want to do that. Where you've got very high carbon existing forests and peatlands, it's really important to keep those in place, because if you do cut them, it will take a number of years of growing and doing the bioenergy to actually get that carbon back. So it's called carbon debt. Could be more than 100 years if you cut down high carbon ecosystems for bioenergy. Where you've already got plantation forests, often they're going to be cut anyway, you've also got lots of forests that really, as they reach maturity, stop growing. So actually,